A single wafer, one processor design, dense and modern, submitted to two factories on opposite sides of a geopolitical fault line. One factory sits in Hsinchu, Taiwan, with decades of process refinement and the most advanced lithography machines on Earth. The other sits in Shanghai, running a workaround that Western engineers once said could not work at all. The bullish case holds that Shanghai has closed the gap enough to matter. The skeptical case holds that the wafer coming out of that second factory is a fundamentally different product, one the market will ultimately refuse to take seriously. 4 rounds decide which case survives: process node on paper, yield and what actually ships, capacity and scale, and the customers who vote with purchase orders. The restriction designed to freeze one competitor in place instead forced an engineering detour that partially proved the competition alive, while widening every other dimension of the contest. That is the tension this analysis is built to resolve. Take the first dimension. The bullish claim is that Semiconductor Manufacturing International has demonstrated a 7 nanometer class process node without extreme ultraviolet lithography. Analysts who purchase commercial devices, remove the packaging, and examine the silicon beneath have confirmed feature sizes consistent with that node generation. The gap, measured in generations, has visibly compressed. That is a real result. The counterclaim is that a node label is a marketing unit, not a physics measurement. What the Shanghai foundry achieved required layering multiple passes of older, deep ultraviolet exposure to approximate what a single extreme ultraviolet pass produces at the Taiwanese foundry. The transistor density may look comparable on a datasheet. The process complexity, the defect exposure surface, and the power efficiency profile are not comparable. Analysts who have examined die photographs from that process note that the layout rules require more conservative spacing, which costs silicon area, which costs performance per watt. The evidence lands in the middle. Reverse engineering reports, most prominently work on a Huawei processor released in late 2023, confirmed 7 nanometer class feature sizes at the Shanghai foundry. The company has published no yield figures and no transistor density data. The Taiwanese foundry's comparable node was in high volume production years earlier and has since been superseded by 5 nanometer, 3 nanometer, and newer generations. On the narrow question of node label, Shanghai proved the floor is higher than Western policy assumed it was. On every underlying dimension of what that label is supposed to guarantee, the advantage remains firmly in Hsinchu. The Shanghai foundry proved it can reach the label. It did not prove it can deliver what the label is supposed to mean. Now the question of what actually ships. The bullish argument runs like this. If the Shanghai foundry is selling volume of 7 nanometer class chips at all, yield is workable. No company sells devices at commercial scale from a production line that fails more than it passes. The commercial release of a product built on this process is itself evidence that the process is not purely experimental. The stronger counterargument is that volume and yield are not the same variable. A foundry can ship a commercially meaningful quantity of chips at low yield by pricing yield loss into the wafer cost. Supply chain analysts have suggested that the Shanghai foundry's advanced node yield sits substantially below the Taiwanese foundry's equivalent mature node yield, though no independent auditor has confirmed a specific number, and the analyst estimates vary enough that any precise figure would be false precision. A low-yield process is not a competitive process. It is an expensive workaround that passes its inefficiency directly into unit cost. The technical reason is not in dispute. The multi-patterning approach requires more process steps per wafer than an extreme ultraviolet-based process. Each additional step is an additional opportunity for a defect. The Taiwanese foundry's mature nodes have been run long enough that defect density is understood and minimized. The Shanghai foundry's advanced node is younger, more complex per wafer, and operating under equipment constraints that prevent the kind of tool upgrades that normally drive yield improvement over time. Until independent verification arrives, the bullish case on yield rests on inference from commercial shipments, not on measured output data. That inference may be correct. It has not been proven. This round goes to the skeptics. The third dimension is where the structural argument becomes decisive. The bullish claim is that the Shanghai foundry has been expanding. New fab construction across multiple Chinese cities, State capital directed at domestic semiconductor manufacturing. Capacity is a buildable quantity, and the government funding is real and documented. The counterclaim is that leading-edge capacity is not a construction problem. It is an equipment problem. The Shanghai foundry cannot purchase extreme ultraviolet systems. The Dutch lithography maker, acting under export controls coordinated with the United States and allied governments, has confirmed it has not delivered those systems to Chinese customers. The multi-patterning workaround that enables the 7-nanometer class process consumes dramatically more deep ultraviolet machine hours per wafer than an equivalent extreme ultraviolet-based process would. More tool time per wafer means lower effective wafer output per installed tool. The Taiwanese foundry, running extreme ultraviolet at scale, produces leading-edge wafers at a throughput the Shanghai foundry physically cannot match under the current equipment environment. Here is where the dissent deserves a real hearing, because the case against this verdict is serious. Export controls have historically produced the ingenuity they were designed to prevent. The multi-patterning achievement is exactly that kind of forced ingenuity, and there is no guarantee the pattern stops there. There is no independent data confirming where yield actually sits, which means the skeptical case on yield relies on process physics inference, not measured output. The Chinese government has the capital and the political will to subsidize below-cost production at scale, which disrupts the normal economic logic that limits low-yield operations. The ecosystem gap in design tools and process documentation is a software and documentation problem, not a physics problem, and software problems close faster than equipment problems. A careful analyst could look at the same evidence and score the yield round as contested, award the customer round more generously given the scale of captive domestic demand, and reach a conclusion that the gap is large, but not structural. That reading is coherent. It is also the reading that requires believing subsidized production at constrained volume eventually generates the learning curve improvements that commercial volume at scale normally drives. That is an assumption. It is not an established pattern in semiconductor manufacturing at the leading edge, where learning curve gains have historically depended on running large numbers of wafers through a stable process, not on running fewer wafers through a more complex one. The equipment ceiling is not a pricing problem or a funding problem. It is a throughput physics problem, and it caps how many advanced wafers the Shanghai foundry can ever produce per month, regardless of how much concrete gets poured around the fab. That ceiling is structural. Round 3 goes decisively to the Taiwanese foundry, and it is the round that matters most, because volume is what funds the next node. The fourth dimension is customers. The bullish case is that Chinese domestic demand for advanced chips is enormous, and under export controls, those customers cannot reach the Taiwanese foundry. Huawei, domestic cloud builders, device manufacturers, automotive suppliers. The Shanghai foundry does not need to compete for orders from Apple or from the large American chip designers. It needs to capture the demand that is being forced onshore by the same restrictions that constrain its equipment. The customer base is, in a meaningful sense, captive. The counterclaim is that captive demand is not the same as sufficient demand. The customers forced to the Shanghai foundry are designing products where performance per watt and die area determine commercial success. A chip that costs more to fabricate because of lower yield, occupies more die area because of conservative layout rules, and runs less efficiently because of multi-patterning overhead is a chip that loses in the markets it actually competes in, including Chinese consumer electronics, data centers, and domestic artificial intelligence infrastructure. The design tool ecosystem around the Taiwanese foundry's advanced nodes is mature, supported by every major electronic design automation vendor, and documented across years of production experience. The Shanghai foundry's advanced node process design kit is less mature, less supported, and represents friction for any team that previously built chips in Hsinchu. The evidence on this round is split. The Huawei processor built on the Shanghai foundry's advanced node is a real commercial product. It sells. Analysts who have benchmarked it against chips built on the Taiwanese foundry's processes have noted measurable gaps in performance per watt. Chinese cloud and artificial intelligence infrastructure companies have, where export timing permitted, stockpiled chips built at the Taiwanese foundry. That stockpiling behavior implies a preference the market has not fully abandoned, even when the alternative is available domestically. The Shanghai foundry has the customers it needs to survive and expand. It does not have the customers whose performance demands and margin payments fund next-generation process research and development. This round splits. The verdict is not close on the overall contest, but it is more complicated than the export restriction framework assumed. The Taiwanese foundry wins. The gap is measured in years on process node, in significant multiples on yield and effective capacity, and in an ecosystem advantage that compounds with every additional design tape-out. The restriction on extreme ultraviolet systems has not stopped the Shanghai foundry from producing advanced chips. It has capped how many it can produce, at what cost, and with what efficiency, in ways that the foundry cannot engineer around without equipment it cannot obtain. Where the gap has closed, node label, domestic customer capture, and the raw engineering credibility of executing multi-patterning at 7 nanometer class at all. Where the gap is structural, tool throughput, leading-edge wafer volume, and the global customer base whose orders fund the next generation of process development. The wafer that set out from Shanghai proved something, just not what its manufacturers needed to prove. Which round did this analysis score wrong? If you think the yield gap at the Shanghai foundry is closer to the Taiwanese foundry's numbers than the equipment argument implies, make that case in the comments. That is the round where the verdict is most vulnerable, and the data to challenge it is genuinely not in the public domain yet. If this kind of forensic breakdown of contested industrial questions is what you come here for, subscribe and turn on notifications. The next contest is already being filed.